Section 4.5, Indeterminate Forms and L'Hopital's Rule. Suppose we are trying to analyze the behavior of the function, and let's say that we call this function f of x, which is equal to the natural log of x over x minus 1. Okay, now although f is not defined when x is equal to 1, we need to know how f behaves near the value of 1. So in particular, we would like to know the value of the limit as x approaches 1 of the natural log of x over x minus 1. Now, in computing this limit, we can't apply law 5 of limits. The limit of a quotient is the quotient of the limits from section 2.3, because the limit of the denominator is 0. In fact, although the limit in definition 1 exists, its value is not obvious because both numerator and denominator approach 0, and 0 divided by 0 is not defined. So in general, if we have the limit of the following form, where we have the limit as x is approaching a value of a function f of x divided by g of x, where both f of x approaches 0 and g of x approaches 0 as x is approaching a, then this limit may or may not exist and is called an indeterminate form of type 0 divided by 0. We met some limits of this type in Chapter 2. Now, for rational functions, we can cancel common factors. So, if we have the limit as x is approaching 1 of the function, let's say x squared minus x divided by x squared minus 1. So what would happen here is that we would factor. So we would have x times x minus 1, and in the denominator we have x plus 1 times x minus 1. And then what we get is now we can simplify this limit as x approaches 1, because we can simplify the x minus 1, and what we get is x over x plus 1. And so now when we evaluate that limit, we get a value of 1/2. Okay, so we used a geometric argument to show that the limit as x approaches 0 of sine of x over x was equal to 1. Okay, but these methods do not work for limits such as, again, number 1. So in this section, we're going to introduce a systematic method known as L'Hopital's rule for the evaluation of indeterminate forms. So, another situation in which a limit is not obvious occurs when we look for a horizontal asymptote of f and need to evaluate the limit, where the limit of x is approaching infinity of the natural log of x over x minus 1. Now, it isn't obvious how to evaluate this limit because both numerator and denominator become large as x approaches infinity. So there is a struggle between the numerator and the denominator. If the numerator wins, the limit will be infinity. If the denominator wins, then the answer will be 0. Or there may be some compromise, in which case the answer will be some finite positive number. So in general, if we have a limit of the following form, where we have the limit, again, as x is approaching a of a function x in the numerator divided by a function g of x, then where both f of x approaches infinity or negative infinity and g of x approaches infinity or negative infinity, then the limit may or may not exist and is called an indeterminate form of the type infinity divided by infinity. Now, we saw this in section 2.5. That is the type of limit that can be evaluated for certain functions, including rational functions, by dividing the numerator and denominator by the highest power of that occurs in a denominator. So, for example, right, if we have the limit as x is approaching infinity of x squared minus 1 divided by 2x squared plus 1. So we have a function in the numerator and a function in the denominator. Okay, and so we're going to divide the numerator and the denominator by the highest power in the denominator. So we're going to get 1 minus 1 over x squared divided by 2 plus 1 over x squared. And so therefore, when we evaluate this limit, we're going to get 1 minus 0 over 2 plus 0, which gives us 1/2. Okay, so this method does not work for limits such as 2, but L'Hopital's rule also applies to this type of indeterminate form. So, L'Hopital's rule. So suppose we have a function f and g that are differentiable, and g prime of x, which would be in a denominator, does not equal 0 near a, except possibly at a. So suppose that the limit as x approaches a of f of x is equal to 0, and a limit as x approaches a of g of x is equal to 0, or that the limit as x approaches a of f of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is approaching plus or minus infinity. In other words, we have an indeterminate form of the type 0 divided by 0 or infinity divided by infinity. Then what we can do is we can apply L'Hopital's rule. The limit as x approaches a of the function f of x over g of x is now going to become the limit as x approaches a. We can take the derivative of f of x to be f prime of x over g prime of x, if the limit on the right side exists or is infinity or negative infinity. Now, discussing L'Hopital, L'Hopital's rule is named after a French nobleman, the Marquis de L'Hopital, from 1661 to 1704, but was discovered by a Swiss mathematician, John Bernoulli. You might sometimes see L'Hopital's rule spelled as L'Hopital, but he spelled his name L'Hopital with an S, as was common in the 17th century. Okay, now, note 1. L'Hopital's rule says the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. It is especially important to verify the conditions regarding the limits of and before using L'Hopital's rule. Now, L'Hopital's rule is valid for one-sided limits and for limits at infinity or negative infinity. That is, as x approaches a, can be replaced by any of the following symbols: x approaching a from the right, x approaching a from the left, x approaching positive infinity, or x approaching negative infinity. Now, note 3. For the special case in which f of a is equal to g of a, which is equal to 0, then f prime and g prime are continuous and g prime of a does not equal 0, it is easy to see why L'Hopital's rule is true. So in fact, using the alternative form of the definition of the derivative, we have the following. So if we have the limit as x approaches a of f prime of x divided by g prime of x, then this is going to equal now f prime of a divided by g prime of a. Okay, which means that the definition states that if we want to find the limit as x approaches a, then we have f of x minus f of a over x minus a divided by the limit as x approaches a of g of x minus g of a over g minus a, which then equals the limit as x approaches a of f of x minus f of a over x minus a divided by g of x minus g of a over x minus a. And so what happens is now the x minus a's are simplified. So now we have the limit as x approaches a of f of x minus f of a divided by g of x minus g of a, which then actually equals the limit as x approaches a of f of x divided by g of x. Okay, now the general version of L'Hopital's rule is more difficult. Its proof can be found in more and advanced books here, but here is somewhat of a proof here. Okay, now if we take a look at this figure, let's take a look at the one on the left and the one on the right. So here we have the one on the left. Here is the function f, and there's the function g, and there's the value of a. Now over here, if we look at the curve, the tangent here, y is equal to m1 times x minus a, and then here's y is equal to m2 times x minus a. So this figure suggests why L'Hopital's rule might be true. The first graph shows two differentiable functions, f and g, each of which approach 0 as x is approaching a. Now, if we were to zoom in towards the point a0, the graphs would start to look almost linear. But if the functions actually were linear, as in the second graph, then their ratio would be the following: m1 times x minus a over m2 times x minus a, which is equal to m1 over m2, which is the ratio of their derivatives. This suggests that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x.